Welcome everybody to this overview of imagery capabilities within ArcGIS. My name is Günther Dörfel. I'm a member of the global imagery team here in Europe, and I'm working here primarily with the distributors, partners, and you customers. And I'm very happy to share some information here with you. So unfortunately, still not being able to do that in a conference room in a more interactive way. But please feel free to reach out if any of the topics that we touched today need some clarification or a deeper dive into some of the capabilities, architectures, or best practices. So let's dive right into our workshop. As I'm sure you have seen, we at Esri are convinced that a geospatial nervous system will play a key role in better management of our planet's dwindling resources and the challenges we face in many domains and situations. Let's only cite the SDGs here. It's not a coincidence to see sensing as the starting point to capture, monitor, and process live data so that we can learn, draw conclusions, and respond to them. Another way to put this is to state it all starts with measurements and observations, recent and historical, allowing us to enter this never-ending cycle of analysis, action, and then measuring again to understand the effects of our action. So this goes along very well with the sensing and the understanding and responding order in the previous slide. To do this with all different kinds of data, bringing them all together, allowing them to be used jointly, derived from each other, or simply understanding them as representing often the same information in different ways. Just a little example to start from the left side. One image is an image. The images of a time period and maybe different observations are a multidimensional data set. As you will see later, if those images are overlapping aerial photos, they might end up becoming a highly detailed 3D city mesh, which can become even better if LiDAR data is a second source of input to the model. The whole idea of the ArcGIS system is to enable this integration. And I want to mention it here right in the beginning, as our coming focus on imagery should not make us forget this. All of this needs to be and can be combined for new insights from diverse data sources. Talking about imagery in the special setting of this conference here brings many important topics to mind. All of them are multi-scaled as they start out in virtually every village, field or forest and end up being accumulated to global indicators. It is a question of scale and resolution in time and in space. So we can go down to the project level here with the notion of probably a single drone capturing highly detailed data for a limited area, but very timely and fast. And again, we could do the same thing, usually much coarser on a global scale. And the same applies to the analytical methods you are using. Methodology keeps changing. It becomes faster, capable of processing more information with less human interaction, and using your expertise, this is leading to new approaches to problems, to new insights, but also to new challenges. For all this, remote sensing is a key part of the sensing prerequisite defined, which leads us to the work done at Esri to support your multitude of requirements. There are many different ways to conceptually structure the building bricks of a comprehensive imagery platform like ArcGIS. I personally like this notion, which clearly shows that a strong image management foundation is key to all the other topics. It is what we use ourselves to offer ready-to-use content. It allows you to perform predefined map production workflows efficiently, and it is an open framework for any kind of any combination of analytical functions, and it serves the data to a wealth of generic and specialized, local, web-based and mobile application and clients and APIs. The ArcGIS imagery capabilities are constantly evolving in all of the areas I showed you. Hot topics today being GeoAI, but also 3D data and multi-temporal analysis, structured observation management, or the analytics of point clouds. In this and the previous two slides, the content topic here on the lower left side seems like a little addendum. It is not. Especially with imagery, the content topic is a topic of mass data, a constant stream of updates and, here very relevant, a topic of cloud storage and access. At the same time, the capturing devices are getting more affordable, smaller, ground-based, and the demand is to be able to fuse data of different origin into one dataset. Think about edge computing and smartphones running AI or terrestrial LiDAR. But first, let's take a look at some of the content offerings that you will find when you use any of the ArcGIS product. I want to start off in the browser and have a look at the ArcGIS Living Atlas of the world. The unique capability of this system is that it offers a lot of authoritative data that we host and also maintain with contributions from many organizations and countries. But you can also share your data sets through this system, and this ranges from, as you can see, imagery to infrastructure data, environmental data sets, and the very relevant base maps that we offer. If you've ever been in any of our products, you know the base map section that offers you to quickly switch between underlying map templates. But I want to make you aware of the fact that there are many more than you usually see in the products. So ranging from pseudo-historic antique map displays to different versions of the world imagery for different purposes, to content compiled by other Esri organizations specifically for their countries. There is a lot in the base map section that you can use and that you can adapt and give it your own flavor. This is definitely not the end of it. In the imagery space, it's important to note that we maintain large collections of imagery and, as I said before, different versions of it optimized for clarity or as background maps and with or without labeling, plus huge collections of spectral imagery like a global Sentinel-2 archive, the US NAIP offerings in collaboration with Planet, some views of the Planet daily imagery, but also Landsat, NOAA datasets, and so on. Some of them being available also as app templates for you to use. You can use any of those datasets just by going here, and then after you check potentially on the item displays, you just open this in a map viewer and you're ready to go. Now, whilst the web and usage of the web is definitely the most important trend today, there's also the desktop products for very flexible high-end analysis. And I want to look at the same section in the desktop area next, so you can just see that it's really part of the platform. So as you can see here, we have the same selection of base maps, a selection that you can modify and add some of the ones that I've showed you before. We stick with the topographic base map for a moment and start adding some of the data we've seen before. In the web, I had added the Firefly sort of reduced intensity imagery. I will do the same thing here. Add the Firefly layer to the data. And for the purpose of looking in some detail, let's get closer to Spain and then add another data set from those live feeds. Let's take this satellite derived data set. Let's go for the MODIS one in that case. And we can see there's some reported fire activity all over the place. There seems to be a little cluster here in that area. So why don't we go in? You see the responsiveness of that. Now, if we want some more recent data from a different sensor, say from Sentinel-2, we can do the same thing again. We search for Sentinel, sorry. There we get the Sentinel-2 views. We add this in, overlaying this area. And as you can actually see, there is one of those fires reported here. There's a wealth more of data in here. One thing that I want to make you aware of, and quite an important and rich data set, is we maintain a world terrain data set that can be very useful for many applications, and other derivatives and collections of terrain data, which can be the basis for any runoff, watershed, whatever analysis on larger scale. And with that, given the short time we have, I want to leave the content section and move over to the next topic. So after looking at some of the content, we start looking at, well, some of the systems that generate this content. And we'll start off with the left side of that slide, reality capture and 3D data from imagery and LiDAR. And we'll actually begin with drone processing in the cloud. SiteScan is a full-blown software as a service solution. At the same time, it's connected to ArcGIS Online Enterprise and your local desktop. Its mobile flight planning app allows you to take the know-how of drone specialists to the field, optimize data capture and drone use depending on the task at hand. Cloud-based processing and data storage guarantees scalability and prevent you having a processing backlog when it's most important to be timely, like after a landslide or a flood or something. Through integrated visualization and analysis tools, SiteScan can be both. It's the all-covering solution or the automated scalable pre-processing engine. Let the pro do the presentation here. See a recorded presentation from Jeremiah Johnson for the UC last year that shows the workflow from mobile app to office analysis after processing the data.
I'm Jeremiah Johnson, Imagery Solutions Architect for Esri, and I'm excited to demo for you today a new product within the ArcGIS ecosystem, SiteScan for ArcGIS, an integrated, end-to-end, cloud-based solution for your drone workflows. We're here at Esri's Redlands headquarters, and we're going to do a quick flight of this building to show how SiteScan can take care of the autonomous flight, image processing, and analysis. To plan the flight, we're going to take our iPad app and define the structure of the building using layers brought in from ArcGIS Online. Once I've defined the structure, I then define the offset from the structure. Notice that as I adjust my offset, the data on the bottom of the screen adjusts as well, reflecting my changes. Once I'm happy with my flight, all I have to do is save the flight plan. Now this flight plan is saved in the cloud, and anybody with a SiteScan operator license will be able to execute it. Looks like we're good to go. Let's go, Mike. The drone takes off straight up to the designated travel altitude. Once there, it makes its way to the first waypoint. Since this is a perimeter scan, the drone flies sideways with the camera pointed at an oblique angle to be able to completely capture the walls and roof of the building. While our drone is performing its mission, I have data from a previous flight. We'll use this data to show the post-flight workflow. Once the images are associated with the flight, I press Upload to Manager. The flight will immediately start processing using Elastic Cloud architecture. In 30 to 50 minutes, I'll receive an email saying the processing is completed. Back at the office, opening the project, I can view a list of all the flights that happened here. Let's open the most recent. I want to inspect the solar panels on the top of the building. To do that, I open the Photo Inspect tool on the right-hand side of the screen and click anywhere on the map. SiteScan will bring up the latest drone photo. But building inspection is not the only use case. Let's go to a construction project. A few miles from here is the San Bernardino International Airport. On the north side of the field is a large construction project where they're building a GeoAI center as well as a new Amazon Air regional air hub. On the left-hand side of the screen, I have layers like the original drone photos or 3D data like the contour or elevation model. I also have access to a volumetric model where I can see the latest updates of the earthwork, as well as a point cloud view where I can make 2D and 3D measurements. I'll also use this map to update my stakeholders. I can do that in one click by pressing Upload to ArcGIS Online, where it will be immediately available to my organization. SiteScan for ArcGIS is a complete end-to-end workflow, assisting you in planning autonomous drone flights to dissemination in ArcGIS Online.
Let's move on to a technology that can cover larger areas and fuse different input. Not only in its native home range, mapping agency-style surveys or aerial survey companies, the Shore for ArcGIS solution can add additional value to comparable workflows, this time flown with photogrammetric cameras and precision, and potentially also including additional point cloud data. Your interest could be a historic city center, a landslide, uncharted settlements, or else. If high-precision digital surface models, true ortho photos, point clouds and meshes are what you need, watch this. While the process of creating the results is mere number crunching, the results itself are visual and important for many workflows. Look at this example starting out in the city of Frankfurt, Germany. This is a base map view of satellite-derived imagery of Frankfurt. You can see the building lean of the high-risers here, and the visual impression is sort of plastic, but in terms of precision and deriving exact height measurements and positional accuracy, this would be critical. If I overlay the result of a Shore processing of 8 cm urban mapper flight, you will immediately see the difference. All lean is gone, and a real measurable position for every single point of every single building or land element can be derived from that imagery. As important as the image representation, probably even more important, is the elevation derived from this data set with high precision. Again, at every XY coordinate, there's an exact Z coordinate that you can get from this data. Just as a side note, you can create like many different interesting derivative products from that elevation information. But what most people are interested in is the combination of what is done from the elevation information and the aerial information. To see that in very high detail, let's move over to the city of Munich. While this looks like an aerial image in a fall situation, it's actually a high precision three-dimensional model of the city. As we zoom closer, you see that the level of detail increases, and if you look at the narrow road segments, and let's just move on to that building a little closer, even very close to the ground, you can see how good the representation of the terrain is. Well, but this is not only a visualization, this is real 3D information. So if I, for example, open a new measurement, let's actually put the church in a good position to see the ground and the top of the tower. So let's start a new measurement. You can see that I can derive a position in this terrain to my liking. So I try to hit the floor here. and then I measure up to the absolute top of, that's about where it is, of the church tower. And as you can see, it gives me exact elevation positions for any point on the map. Now, how can that be used in real life? Well, one example, and we move back to Frankfurt here, would be this. This is, again, the flat aerial image situation now in a 3D position. The result of Shore, in fact, is also a point cloud, just to fill that in that position. But let's move back to the mesh location that we've seen before. Now, this mesh, as I said, has real 3D information. So if we have additional layers, like, for example, the water level on an assumed 100-year flood situation, we can actually use that together with the mesh, identify the building impact this is going to have in circumstances, and then discuss countermeasures and potential insurance risks, or whatever the topic of that analysis is. By the way, since we're talking about these 3D meshes and their use here in a browser environment, I want to introduce to you another client that can work with this 3D information. This is ArcGIS Earth, a free client that anyone can download. It works very fine with KML data and other data sources, and it's perfectly capable of taking exactly that mesh that we've seen in this web application and fluently work with it on your local PC. And with this, let's move back to our journey. You've seen me presenting the high-resolution Frankfurt ortho image and the 3D mesh in a browser and also in ArcGIS Earth. This is a perfect moment to speak about data management and dissemination scenarios with ArcGIS Image. Here on this slide, you can see a very small, brief representation of local image management and data preparation done with ArcGIS Pro, Mosaic datasets, GeoImage collections, everything. It also shows the long time existing ArcGIS Enterprise server installation that you can have on your local premises or in the cloud, together with ArcGIS Image Server to serve dynamic tiled and hosted imagery and do additional tasks like raster analytics and ortho mappings on them. We have now added additional offerings to this ArcGIS Image family, which is ArcGIS Image for ArcGIS Online. First version just released in March, which allows you to store imagery and tiled image services, and in the near future also dynamic image services, straight in your ArcGIS Online account. We will also add something called ArcGIS Image Dedicated, which are dedicated machine instances that we maintain for you while you have full control of all data and processes on it. But for now, let's stick with ArcGIS Image for ArcGIS Online. Please follow a demonstration done by Johan Yoon during the Fed GIS conference in March, right before the release of ArcGIS Image for ArcGIS Online.
Many organizations in the federal government have the need to share image services between agencies and the public. This can occur during daily business operations as well as in times of emergencies. The new ArcGIS Image for ArcGIS Online beta provides hosted imagery capabilities along with visualization and raster analytics in the cloud. Last year, approximately 10,000 fires burned more than 4.3 million acres in California. To understand the impact and severity, we'll analyze the area near Santa Rosa using the new ArcGIS Image for ArcGIS Online. For our analysis, we'll be using a collection of satellite images that cover this area. These images that I currently have locally can now be hosted directly to ArcGIS Online. Let me show you how. Images can be hosted as static tiled image layers or dynamic imagery layers that support dynamic mosaicing and on-the-fly server-side processing. From the interface, users can select the layer configuration, choose the data type, and fill in additional information such as the processing template and more. By simply dragging and dropping the image files and their metadata and filling out the item description, these image layers will now be hosted in ArcGIS Online. Fast forwarding a few minutes, once the data is uploaded, we can add it to our map and begin our analysis. This is an image near Santa Rosa after the fire. By changing the band combination on the fly, we can now have a better look at the impacted area, indicating loss of vegetation in orange. We'll continue our analysis by applying a raster function template, which will classify the area by burn severity. The raster function editor in ArcGIS Online provides 153 raster functions out of the box that can be chained to create a complex model. These raster function templates can be shared and used across desktop, enterprise, and now even on ArcGIS Online. Once the template is loaded, all you have to do is click on Run Analysis to get your results. In the interest of time, I have it generated in advance over 3,000 square miles. The high burn severity is shown in orange and lesser severities in other colors. Now, one of the questions that you might ask next is how many structures were in the path of the fire? And if you didn't have the building footprints previously mapped, we can leverage the deep learning capabilities in ArcGIS Online to extract the building footprints. To get started, let's go to the new raster analysis tools, select deep learning, and in our case, detect objects using deep learning. Using high-resolution worldview imagery provided by Maxar, and going to the Living Atlas, we can select from a library of ready-to-use deep learning packages that include land cover classification, road extraction, human settlement detection, and more. For our use, we'll select building footprint extraction. Let's take a look at the results. The model was able to extract tens of thousands of building footprints in just a matter of minutes. We were able to determine the number of buildings within the burn perimeter. This was just one example of using ArcGIS Online with hosted imagery. Now let's take a look at a different topic and at a national scale, conservation. The 30 by 30 initiative is about preserving 30% of our lands and oceans by the year 2030 to balance the physical, biological, and cultural assets of our environment for a sustainable future. Here are the areas already protected within the US. Roughly 12% of the lands and 23% of the oceans correspond to an assigned GAP status 1 and 2, which requires permanent protection of its natural state. Overlaying managed federal lands, we can see a broader area covered, color-coded by managing agency. In order to achieve our conservation goals and reach 30%, we may want to identify areas of the federal land suitable for additional protection, and new areas across the US with a high priority in our conservation efforts. To answer the question where to focus our efforts, we collected available resources on the Living Atlas to build a national inventory of information layers which will help us define the characteristics across the US. The first example dataset is NLCD, Natural Land Cover Dataset, created by multiple federal agencies using different variables like vegetation type, agricultural use, and development density. The next dataset created by conservation scientist David Theobald shows human modification across the US. The darker the red, the larger the human influence on the area. The third example shows biodiversity importance generated by NatureServe. The brightest colors indicate where multiple imperil species occur and are currently not safeguarded. These are just 3 examples of the information that we loaded into ArcGIS Image for ArcGIS Online to create a collection of 27 layers describing the land characteristics across the US. Using raster analytics, we created the first national map of minimally disturbed natural areas, also known as green infrastructure. This layer is not just a visual description of the location, but also an information-rich data set that allows us to perform analytics and help us answer where to prioritize our conservation efforts. Conservation priorities are not always the same for everyone, and as a result, it requires input from multiple stakeholders. This web application allows us to leverage the benefits of the dynamic imagery layer and help us narrow down potential conservation areas based on different scenarios. Let's assume that we would like to expand the conservation areas around Yellowstone National Park. Looking at the federal lands, the immediate vicinity is managed by the Forest Service, so we'll prioritize forests and biodiversity for this scenario. The result of this analysis is a weighted overlay, highlighting areas of high conservation priorities in dark green. Now let's take a look at a different scenario, prioritizing wetlands instead of forests. We can change the weights and get an alternative answer. Let's try one more, wildlife conservation corridors. When we start to look at this from a larger context, we can discover the natural network forming pathways across the US, like this one that connects from the Grand Teton to the Upper Green River Valley and south into Colorado, which happens to be the largest pronghorn migration corridor in Northern America. As most of this corridor falls around BLM lands, this analysis shows possible areas for additional federal conservation and protection. These were just two examples of ArcGIS Image for ArcGIS Online providing managing, hosting, visualization, analytics, and sharing capabilities at any scale, conveniently and efficiently in a software-as-a-service environment. Thank you.
We have now highlighted some examples of reality capture and data storage and management. Now, let's look at selected analytical capabilities. There is a wide range of offerings, ranging from implemented full workflows, for example for hydrological modeling, to hundreds of single functions to be combined to workflows. And all this can be done through interactive tools in APIs like Python or Python notebooks and exposed through services. Let's just pick two current hot topics, GeoAI and multidimensional data. Starting with GeoAI, or better, with the open deep learning integration in ArcGIS. If I would call us geo people, then we have a big advantage. We have data. This data qualifies for the much sought after training and validation data for deep learning. All tools and all workflows for all this have always been part of ArcGIS. So we can do data labeling, data preparation, train models and run them, but we can do this in a scaling environment, and we also have all that's needed before and after. We have the data management side behind it, the ingestion and handling of input data, and then downstream we have more than 1,500 tools and functions to process, analyze and work with this data and distribute, share, disseminate it through groups with identities, through applications and access, even with mobile devices. Let's just take a look at examples of this deep learning and how it could be implemented. I want to start out in the desktop and just show you a little glimpse of the geoprocessing environment that enables you to do deep learning, again in similar fashions also on the server. You can train deep learning models, then run inference in different versions with different frameworks behind it. All this can make use of a scaling environment with several processing units, and also use graphic cards for much higher performance in deep learning, as most of those models really rely on GPU usage. So how does that actually look? If I want to use the example of building footprint detection from aerial imagery. I could just go to my tools environment. I could again search for the deep learning tools. I could then say I want to detect objects using deep learning with an input raster, a specification of the output objects, and define the deep learning model that I want to use, give it additional properties. That's nice, and that would get me something like this. If the model is fine, I would get some output of building footprints. Well, it's not just that, it's coming with additional attribution. So as you can see, I have overlapping results from a tiled approach to that with different confidence levels that represent what I want to do. Remember that I said the good thing is we have a lot of downstream tools to work with this data. So in ArcGIS, I can start cleaning that up, apply additional processes, and what I get in the end are polygons that are quite good representations of the buildings. Looking at this from a workflow perspective, this is how it would actually look like. You can see that only step 1 is really detect objects using deep learning with several inputs, and the rest are those downstream tools that dissolve the data and that regularize the building footprints for the final output. So this is a real workflow that includes the data management part before this, the training of the model, the final inferencing, and then the post-processing of all the data that's in here. Now, this is the model builder approach to it. You also have, in similar fashions, as I mentioned, the approach of doing this with Python notebooks, and I have examples in here for a detection model of power lines, or a little down there using LiDAR data to identify trees. Where do I have those from? Remember that we were looking at the Living Atlas before that already. If I search here for deep learning models, and I actually do that with the abbreviation we have for those packages in here, you can see that we've published a number of ready-to-use deep learning models on the Living Atlas. This building footprint detection, where you just saw an example with the results, land cover classification based on Landsat and Sentinel, road extraction, and some models based on LiDAR data like this power line classification or trees and others. And this is a list that we're definitely gonna extend over the near future. So to sum up on the deep learning side, what we've done, we've integrated available frameworks of relevance. And that's basically happening on the Python level, so you're free to use whatever environment and analytics you want to use in here. Then we've connected it to standard data types in ArcGIS that you can use together with those models to perform specific deep learning tasks. Those tasks might be available already for you as shared models that you can just use the way we provide them, or you use them as the starting point and improve upon them. And all this is exposed through Python notebooks, desktop use, server use, APIs to make it available or integrated into your own workflows. There is a separate workshop on deep learning in ArcGIS during this conference. Please check your agenda to see when this is. Let's move over to the second analytical example I want to give you, which is the topic of multidimensional data. There is an increasing demand to handle large scientific data sets and deep temporal data stacks. Some people want to work with pre-processed so-called image cubes or data cubes. In essence, there are formats out there like NetCDF, GRIP, or HDF that offer these capabilities. But there's also just numerous sensors and independent data that can be added to multidimensional data stacks. And very important for efficient use, they can be handled, sliced, used in a transposed way to make them accessible and performing. I want to show you this using an example that is sort of happening in my home range. I live in a small town called Freising in Germany, very close to the Munich airport. Increasing traffic, like everywhere, has led to a decision to build 2 major bypasses at the northeast and southwest of town. The work is ongoing. It has started several years ago, and it's a good use case for a compilation of freely available Sentinel-2 scenes into a multidimensional dataset. So that's what I did. I collected 30 plus Sentinel scenes and stacked them together. I clipped them to the area of extent I'm interested in and made them available as this multidimensional dataset to ArcGIS. As you can see, this dataset has basically a time dimension. So one easy way to move through time with it is to just go and take the time slider and then watch the different time steps. The 2 rectangles show you the areas where those bypasses are being built during the last years. So you can see in 2015, there's nothing to see from it. And if we move like late into 2019, that's been actually a good time when the bare earth surfaces were very well visible. Those roads that are now accessible were nearly ready. This is the visual way of doing it manually. I can pick any single time slice from that data set, from that multidimensional data set, the same way I'm doing it with the time slider. And I can just get a change between those points in time. And don't get me wrong, this is nothing that is being pre-computed or anything. This is just a function chain. I take 2 slices of time from the multidimensional data set and I compute change. So this is happening as I click the button, as I do it here. I've also prepared a single classifier for that data. So I can watch the same data with only a few classes: forest, then agricultural land, barren land, built-up land, and water. And the classification, same way, happens dynamically on that data set. So if I move along time, whatever time slice I'm ending up with, I get a new classification. This becomes pretty interesting because another way to look at that data is not like we're currently doing it, 1 slice at a time, but to get the information over the whole stack of data. The first way that many people might know is just go here and say, I want to do a stacking through the different bands in that data set. So if you give this a little bit more room, if I take any point and I'm looking for red edge, water vapor, and near infrared, maybe somewhere in the areas where there has been change over the last years, that would look something like this. So just a quick stack through all the time slices, again happening while you see it and giving you a graph of it. Now this becomes a lot more interesting because this is still not self-explaining or takes some expertise to understand. If I go back and query my classified data set. So if I do that same thing here, if I look for the graph that I added to this classified data set, and I pick a point in time and I basically pick the same point again, what you will see is the classification and its change over time. So the point I picked in 2015 was still planted, cultivated agricultural land. Then apparently something changed in the range of 2017. The use has changed from barren land, well, there's still some greenness has been on it, And it's basically now an open stretch of construction that is still, I didn't define any additional classes, that is making a change here and then going into a new phase of what it actually is. I think this shows very well and very quickly how fast this analysis can be done on this data. So here you see this change only happened in 2019, and how effective access to those 39 Sentinel scenes, a few gigabytes of data, can be if you use it in this multidimensional sense. And with that, let's go back to our timeline. We're rapidly reaching the end of the time we have for this workshop. So let's take a last brief look at the ways to visualize and exploit the data that you have using web applications, specialized applications, or tools within existing clients. I want to just highlight 3 more examples, and they span again the desktop and the web. I'll start at the desktop looking at a map in a standard map view. And what I'm going to do right now is I'm going to extend this to include some more data. And as you can see here, I have some videos here. And what I'm going to do is I'm just going to drag over this geo-enabled video into the viewport. So what I have now is 2 views of the same area. You can see an extant rectangle that shows where this video is actually looking at, and you can also see where the camera position was when this video was taken. And when I start moving through the video, you will see that the extent the video covers sort of changes. There is interaction between video and display also in terms of data. For example, I took this example and I quickly sketched in some of the parking areas that are available in here. So what I can do here, I can do the same thing, and I'll have those parking areas integrated dynamically into this video display. The same thing works the other way around. So if I navigate in the video and I see something of interest to me, let's assume it would be this circular area of green space, then I could actually put a point in here, and the point will also appear in the map display. Target of this use of this is quick capturing of information along linear features like roads or compounds like here. And this way of navigating through data in a video is just incredibly much faster than going through single frame images. But coming to single frame images, you might have very, very many single frame images, and you have to navigate through those. What you can see here is bringing us back to drone data. This is a drone flight actually, and the green area you see is the whole area covered by the drone images. I can now query any point in that data set, and it'll inquire which images have been taken in the vicinity, and then start loading up the closest to the point that I had asked for. That's coming from the cloud. And as you can see, there's tons of other images that somehow also contain this piece of information. So if I change my viewing direction, I'll just ask for another image. If you look at the red rectangle here, you can also see where I'm looking to. And when I start zooming into, you will also see on the map display what the extent that I now see in terms of that video coverage is. If we put the capturing device into people's hands, we get something very similar. This is basically the same thing. The whole compound of Esri has been taken in single shots by just a mobile phone. from ground. And if I query a location here, you will immediately see that the perspective that you have is the perspective of a person. So if you think about a construction, manholes, a billboard sign, some damage to something, this is a good way of documenting it and then bringing it into this spatial context. And with, let's say, devices that are offering additional precision, you can add really good measurement capabilities and the likes in here. An application that is being talked about a lot is ArcGIS Excalibur. It's also a web application meant for structured observation capturing. The key element again is that you can make use of the data structures and use the different capabilities you have. What I have here are two oblique aerial shots in its here view from top, but Excalibur can offer you the same data in dual mode, so you have it in the image perspective, like from the point where the plane was and looked at it, and it's essentially the same thing here. If I start doing annotations here in this imagery space, for example, you can see that the same thing will appear in map space as I go. This is meant to detect change and capture information on data that represents a certain situation, and the captured elements will always be linked to the image they came from, including time and who captured them. And this can be distributed easily because it's a web application to potentially many users in one go. With that, we're coming to an end. And the only thing left for me to do is point you to some additional resources. Please check on the web, the products pages, the training materials specifically to imagery and remote sensing, and very important, if you're looking at specific workflows, typical processes, you'll find them documented and a lot of best practices in the workflow section. The only thing that I can do now is wish you a good conference. I hope you all stay safe. I hope we find the time to meet again in person very soon. And I thank you very much for spending the last roughly hour with me and us. Thank you very much and goodbye.